In this little video, we're going to look at ionization energies, and this follows on from our electron configurations. Let's return to our calcium atom, which we were looking at last lesson. So calcium, as we know, has 20 protons and 20 electrons. But when it bonds, we know that it loses those 2 electrons to become a calcium ion and has a 2+ charge. And that's because we've lost those 2 negative electrons. Now that process is going to be endothermic. We've got to put energy in to take those negative electrons away from the attractive force of the positive nucleus. And we call that process an ionization energy. And in fact, there are 2 ionization energies involved for calcium atom becoming a calcium ion, and we'll look at those now. So what is ionization energy? Well, the definition is it's the energy required to remove an electron from a mole of gaseous atoms or ions, and that's a definition you need to learn. So there are different ionization energies. We can have the first ionization energy, and that's the energy, funnily enough, that we need to remove that first electron to form +1 ions. And then we can have the second ionization energy to form +2 ions, and the third ionization energy, and we can carry on. So for calcium, we would have our first ionization energy, second and third, and we can carry on to our 20th ionization energy when we've removed all. So what would a graph of ionization energies look like if we plotted them all for one atom? And again, we'll look at calcium. So we're going to use a log scale. Now a log scale just takes a scale where we have a large range in numbers to make it a little bit easier to handle. So for example, 10 would become 1 and a million would become 6. So let's now look at what it will look like for calcium. So first of all, I'm going to remove my first outer 2 electrons. Those are the ones furthest away from the nucleus, so they're highest in energy, so they're the easiest to remove from the pull of the attractive nucleus. Then I'm going to enter my next shell, and there are 8 electrons in my next shell. And then I've got the second shell, closest to the nucleus, another 8 electrons in there. And finally, the 2 electrons closest to the nucleus. And we see that there are jumps as we change shells. So between the second and third, between the 10th and the 11th, and also between the 18th and the 19th. Now it may look small, but it's actually very large because we are looking at a log scale. Of course, there's going to be a general increase as we remove electrons from the same shell because the ion is becoming increasingly positive as we remove those electrons. And so there are the same number of protons attracting fewer electrons as we keep removing them, and therefore the attractive force of the nucleus becomes larger and it's harder to remove the electrons. So let's look at an example. Which group is this atom in? Now, we don't really want to have to plot a graph because they're quite time consuming and you won't have time in the exam. So the key thing is to look at the jumps as we go through the numbers. So first to second, you can see it's about, I don't know, times 3 or so. Then again, just over 1 or so, 1.5 perhaps. Again for the next one. However, when we get between the 6th and the 7th, you can see there is a huge jump. We go from 13,326.4, that is, to 71,334.2. So that's a huge jump between the 6th and the 7th, and so that is where we're changing shells. So I've got 6 electrons in the outermost shell, those are the ones I remove first, and therefore my element is in group 6. Now, could we just say, well, we've got 8 ionization energies there, so we must have removed 8 electrons and therefore it's got to be oxygen, which is going to be in group 6. Well, we can't, because they haven't actually told us that they finished removing electrons, and they could carry on. There could be an 8th, 9th, 10th, 11th, and so on. So it could equally be sulfur or selenium, unless they actually say that they have removed all the electrons from the atom. So just be careful with that one, and try not to fall into that trap. So we can now look at some trends in first ionization energies. So when we look at trends, we're going to look at 2 trends. We're going to look across a period, and we're also going to look down a group. So let's first of all look across a period. And before we do that, let's have a think, what will affect the magnitude of first ionization energy? So it's going to depend on the charge of the nucleus, the higher the charge, the stronger the attractive force. The distance between the nucleus and the electron, if the electron's far away, it's going to be far less attractive than if it's in a shell closer. And finally, shielding from other electrons. And we'll look at shielding in a sec. So, crosser period, let's go. So there's a little things we need to run through. So first of all, let's look at nuclear charge. And we're going to look at lithium and carbon and neon. As we go across the period, the number of protons in the nucleus is going to increase, and so will the attractive force that the electrons experience. So as we go across there, we are going to increase the strength of the nuclear charge, and therefore we are also going to increase the ionization energy. How about the distance between the nucleus and the electron? Well, we look at the outermost electron. It's actually going to get closer. That outer shell is going to get closer to the nucleus because of the first thing we just looked at. The nucleus has become more positive, therefore it's going to attract the electrons more, and it will be pulled closer in to the nucleus. So that's the same. We're going to increase the ionization energy. And finally, we're going to look at shielding. Now, for shielding, electrons are the ones that get in the way of the electron, the outer electron, and the nucleus. So electrons in the same shell don't stop the attractive force between the outer electron and the nucleus. It's standing side by side. If you think of those ones in carbon, if we just have a quick look over here, we have got this electron here. Now, his view of the nucleus is only shielded by these green electrons. His partner over here is not getting in the way at all. So it's only these that are called shielding electrons. And so the shielding electrons are there. The number is the same across the period. It's going to be 2 for all of them. So we can say that the shielding remains constant, and therefore all those 3 combined mean that the first ionization energy will increase across a period. So lithium will be the lowest and neon will the highest. And of course that makes sense from the chemistry we know. We know lithium is very reactive and it will lose that outer electron very easily. However, neon, very unreactive and is nowhere going to lose that outer electron. So let's look at the trend down a group. And we're going to look at group 1 for this one. So down a group, we are again going to look at the 3 factors: strength of nuclear charge, distance between the nucleus and the outer electron, and shielding from the inner electrons. And we're going to use lithium and sodium to look at these factors. So first of all, strength of nuclear charge. Well, as we go down the group from lithium to sodium, our nuclear charge will increase, and therefore that will also increase our first ionization energy. However, we also have an increase in atomic radius and an increase in shielding electrons. Lithium's just got 2 shielding electrons, sodium's got 10. And of course, sodium's outer electron is in the 3rd shell, whereas lithium's in the 2nd shell, and is hence sodium's electron is further away from the positive attractive nucleus. Therefore, we have one factor which is going to increase the first ionization energy, that's the nuclear charge, but 2 that will decrease our first ionization energy. When we put these values together, we find that the distance between the nucleus and the electron and the shielding from the other electrons increasing outweighs the increase in nuclear charge, and therefore overall our first ionization energy actually decreases as we go down the group. Does that make sense chemically? Well, hopefully yes. We know that sodium is more reactive than lithium because sodium's electron is easier to remove than lithium's. It's less attracted to the nucleus, lower first ionization energy, and therefore more reactive. So let's look at the actual values. And we can see that indeed, as we go across a period, the values do increase for our first ionization energy. And as we go down a group, they are going to decrease. And we can see that as we look from lithium to sodium and neon to argon quite clearly. Okay, so let's have a think now about those odd values. If you see boron and oxygen kind of dip. You'd expect them to be higher than the preceding atom. So we're now going to look in more detail at group 3. So group 3, we'd expect our boron and aluminium there to be higher than the preceding elements in their period. That's because they have one more proton in a nucleus and the shielding has remained the same as far as we are aware, and the atom has got smaller. So why is it that it is actually lower than our beryllium? Well, it's because for the first time we have got an electron in our p subshell all on its own, and the p subshell is of higher energy than the s subshell. Therefore, that electron is going to be easier to remove from the atom, and it's also going to be more shielded by the s subshell from the nucleus. That means that the attractive force between the nucleus and the outer electron in our p subshell is less than we would have predicted it to be, and therefore our ionization energy is less. How about group 6? Well, let's think of the electronic configuration of group 6. They have the first time going to have two electrons paired in a p orbital. So we have s2p4. Now those electrons that are paired up in that p orbital are going to repel each other. Again, although oxygen's got more protons than nitrogen, and therefore we'd expect the first ionization energy to be larger, it's actually lower because we've had to pair those electrons in the same orbital, and therefore they repel each other, and it's easier to remove that electron. So ionization energy, a few main points is you need to know the trend across a period, down a group, and why the first ionization energy of group 3 and group 6 are lower than we'd expect them to be. And when you're tackling these questions in an exam, key thing, you always talk about those three main factors: nuclear charge, shielding, distance from the nucleus, and you wrap them all together and talk about how that affects the attractive force between the outer electron and the nucleus, and finally, how that will affect the first ionization energy.